Hello, and welcome back to another edition of Bentley Nevada's Beyond the Basics webinar series. In today's chapter, we're going to be talking about Vorso, our exciting new torsional vibration transducer system. Before we begin, just want to cover a few different housekeeping items as we get set. You'll notice on your screen there are several different application engagement icons. You can certainly move around, resize. These are leveraged for requesting additional information, addressing questions or asking questions that we will get back to at the end, as well as various other different tools. You'll notice the main presentation, of course, in the center of your screen, which you can enlarge or resize as you see fit. So with that, let's begin. And just as a quick reminder, the Vorso discussion we're going to have today is part of several different webinar series, as you can see on your screen. No worries if you've missed one of these in the past, as they will be pre-recorded and available to you shortly. So let's start. Let's begin today's discussion by introducing our presenters. Today I'm joined by Brian Howard. Brian is a principal mechanical engineer with a bachelor's degree in mechanical engineering from the University of Houston and a master's in electrical engineering from the University of Washington. Brian's focus is on sensor development, algorithms, as well as research and development in our forthcoming products. As for myself, Chris McMillan, I'm a senior product line manager here with our Bentley Nevada business, focusing on the entire sensor portfolio that we have, including our exciting new Vorso development. So let's go. So today's discussion is going to focus on three key areas, with a fourth, obviously, for questions and answers at the end. Section 1 will be around what is torsional vibration. 2, of course, what is Vorso and how do we apply this? How does the technology work? And last but not least, my colleague is going to introduce what are some of the insights, results, and real-world applications that come through. Topic 1, let's get a background and what do we mean by torsional vibration? Torsional vibration. Let's first define the basics. In the vibration world, one of the key vibration that most folks are familiar with is certainly radial shaft vibration. This is leveraging traditionally proximity probes in an XY or 90-degree offset to monitor a shaft's radial vibration. The next key vibration component is axial, and this is, again, taking a proximity measurement, and this time looking at the actual thrust, typically along the Z-axis of the shaft. And finally, getting back to what is torsional vibration. Torsional vibration, in this case, rather than looking at the shaft relative motion in a radial or in an axial direction, this is now looking at the rotational twist, the rotational stresses, etc., of the shaft coming through, introduced by torsional. This is most commonly defined, or a quick example to give a quick visual. If anyone recalls, there's a very infamous bridge called the Tacoma Narrows Bridge that unfortunately failed due to torsional vibration. Now, granted, this wasn't caused by a machine case. In this case, it was wind effects causing this to come through. Nonetheless, it gives you a prime example if anyone wants to remember or recall from their engineering days, that prime example of torsional vibration. So let's get started into a bit more details as we go forward. So one of the most commonly asked questions when discussing torsional vibration in a forum or within industry is, why is this of a concern today? The fact of the matter is, torsional vibration has always been there. We've not been able to measure it, or I should say history has not been able to measure it or adequately measure it continuously, just given previous technologies. However, in the ever-evolving world today, we do have new technologies. One will be introduced today with Vorso that now enables us to accurately and real-time monitor these torsional characteristics that can impact your machine. One of the key reasons that technology has been lacking is the cost of deployment or the lack of robustness for continuous use. With Vorso, we'll get into the details in just a second, but Vorso looks to address not only the cost, the ease of deployment, as well as the continuous use case. One might ask, of course, why would you consider monitoring torsional vibration? You can see on this screen just a few bullet points here that could be leveraged for consideration. One of the most exciting things that we feel Vorso brings to the table is really on that first and second bullet points. One, certainly modeling and, validating the existing machine torsional behavior and comparing that with any potential torsional models, which are based on math and theory or based on a single unit test stand application. But once these pieces of equipment come out in the field and are interconnected, validating the existing torsional model. The second piece, of course, we talk about is that continuous monitoring piece. It's one thing to have a model. It's also one thing to do a torsional check periodically. But the ability to monitor and look for sudden increases or decreases from a variety of different factors that can attribute to the increase in torsional vibration, which unfortunately, in a worst case scenario, there's a quick picture up on the upper right-hand side of what can happen when torsional vibration goes unchecked. That third bullet here, we talk about reducing operating exclusion zones. Now, this is not applicable for every industry, but certainly some industries out there, there are certain zones of operation, speed, if you will, load, where depending upon that torsional mode, if you have that operation, these are called exclusion zones. These are where a customer or the machine, it is highly recommended to avoid operating these zones, certainly to not excite any existing torsional resonances. However, oftentimes these exclusion zones is the optimal zone to operate in for improved efficiency. So there's a large safety factor typically involved that gives a wide exclusion zone. The ability to monitor continuously with Vorso or monitoring torsional vibration can narrow down that exclusion zone window, thereby potentially increasing your operational efficiency. So with that, as I promised, let's discuss in our next slide the application quick examples. So just a brief snapshot of a few applications where torsional vibration is certainly prevalent. This is not an exhaustive list, but is meant to provide an overview of where you may or may not see torsional vibrations that exist today. On the right-hand side, here's a typical example with a typical motor-driven compressor with a variable frequency drive machine. As technology advances, the use of variable frequency drives certainly increases the efficiency of these motors and the output that can result. However, variable frequency drives, by their very nature, they are digital. They're looking to vary, again, the frequency coming through, and they do this in basically a step fashion. Very small to see, I understand, but if you can look at that image on the left, in a perfect world, it would be a sinusoidal wave, if you will, nice and smooth as that variable frequency drive is functioning. In reality, the programming looks to mimic that nice smooth wave, but it does it digitally with small incremental step changes. These are the step changes that can cause and can excite some minute torsional resonances or torsional vibrations, which unfortunately can result in catastrophic failure or damage to a shaft. A second key application with any opportunity out there are certainly any sort of gearbox-driven or machine trains with certainly long shafts. With any startup, of course, there's a lot of inertia, there's a lot of torque applied to that machine train, certainly as it ramps up and gets to steady state load. But monitoring these vibrations is certainly of interest for Vorso. And then last but not least, and again, not all inclusive, one other key example we've seen is certainly typically in the power industry here, where you've got grid instability. So this is basically a prime example would be you've got a power generator on base load. There could be some auxiliary power coming in, whether it's from renewables that hits the grid. The entire grid system looks to, again, dampen out those vibrations coming through on the entire system. These are these vibrations or these grid oscillations, if you will, can cause havoc and can excite resonances even in large steam generators or gas-driven generators. An example of what may cause additionally some of these grid stabilization is if you can imagine yourself in a steel plant, if you've ever been to one, or these arc furnaces where they melt the ore down. These arc furnaces require a tremendous amount of power, of course, to generate and do as they need to do. These tremendous amount of power, arcing by nature, of course, requires, they're short and intermittent, and they come through and they're large spikes on that grid. So the grid has to be able to couple not only these high demand short use cases, but also the everyday baseload use cases as well. There are methods, of course, around this to help mitigate and dampen out these grid oscillations, but certainly if you're not being detected or at least monitoring and evaluating the impact that these are having on shafts and machine trains due to torsional vibrations that can go unchecked, certainly can lead to additional faults and failures in the future, etc. So these are just a few quick examples that we're talking about here. There are many other applications that are out there where torsional vibration can cause and has caused additional machine maintenance, leading all the way up to machine failure. Okay, let's jump straight into our next topic, a little bit about Vorso, what it is, how it works, and why we're so excited about this. Vorso. So what is Vorso in a nutshell? Well, Vorso, by Latin definition, means to twist. And we're excited to introduce this new solution as the next chapter in Bentley Nevada's rotor dynamics. At a high level, there are three key elements combining the best from Bentley Nevada: our hardware, our software, and of course the analytics that goes with it. That of course starts with non-contacting sensors, which if you recall I mentioned cost of installation can be a barrier to entry. The Vorso is a non-contacting sensor, and more on that later. The sensors will then go into our traditional monitoring platforms, 3500, near and dear, our new and just recently released Orbit 60, and then last but not least on this list, an additional opportunity for torsional dynamics and diagnostic services into our Audrey platform. So three different monitoring solutions depending upon the application and the need. The former two, 3500 and Orbit 60, will certainly connect into System 1 for the additional analytics, trending, and overall alarm values across the entire plant and the machine train. So let's next dive into some of the key features we've targeted for Vorso. So a bit more detail, the heart and soul of Vorso is of course the non-contacting sensor. I mentioned it before, but I'm going to mention this again. The non-contacting aspect of these sensor installations allows for much simpler, much more cost-effective, there's much less intrusiveness to the machine in order to deploy this solution. The second key point I really want to emphasize here is that fourth or fifth bullet down. This is a continuous online monitoring solution for torsional vibration. Unlike traditional systems, which are temporary in nature, the Vorso system allows you now to continuously monitor for torsional vibration impacts and elements that affect your machine train. Naturally, given the environment that these are going into, these are suitable for hazardous locations. So with that, everyone's going to be asking, how in the world is Bentley Nevada doing this non-contacting? That's next. So how does the sensor work? How is this being non-contacting? Well, the theory of operation is actually relatively straightforward, and it's based on magnetostriction. What that means here is as you take any metallic shaft, as you apply a torque, basically the magnetic permeability will change. And that's a natural phenomenon that we count upon in order to measure torque and torsional vibration. If you take a shaft and visually twist, you'll have one element of the shaft in tension, while if you can imagine the other element in compression due to that torsional nature. The Vorso probe has what looks like a bridge design, multiple different sense poles that monitors both and takes a look at and senses both the torsional related forces creating tension as well as those that are creating compression. Therefore, we can accurately determine your torsional natural stresses and amplitudes. Okay, I'm now going to transition over to, and again, introduce Brian Howard, who's going to walk us through some actual insights and results you can expect to receive with Vorso's torsional vibration monitoring solution.
Thank you, Chris. Now that you all have an understanding of how the sensor works, we're going to transition into sensor application and operation for turbo machinery. As Chris mentioned, the sensor responds to stress, so we want to locate the sensor where it is most likely to see the highest level of torsional stress. In the absence of prior torsional measurements, a model can be used to identify the likely areas of high stress. There are two common methods for these models. A lumped parameter model reduces the complex components of the mechanical rotor to a system of equivalent mass stiffness elements. This approach allows for well-bounded calculation, the eigenvalues and eigenvectors of the system. The top sketch shows the original machine train, and the bottom plot shows the lumped parameter model. This approach is reasonably accurate for the first few torsional modes, but it's not as accurate for the higher modes. To provide a more accurate estimate of the higher modes, the machine can be modeled in a finite element program. In either case, the system response is typically evaluated for the undamped, free torsional response. Since torsionals on turbo machinery are usually poorly damped, this is a reasonable approximation. Using either the lump parameter or FEA approach, the model output will include the estimated torsional natural frequencies and the mode shapes. The figure on the right shows the estimated torsional natural frequencies highlighted by the red rectangle and the mode shapes as dots connected by lines. The torsional natural frequencies indicate the rate at which the rotor system would naturally twist if it was torsionally perturbed by an impulse event. These frequencies are a property of the rotor system and should not change, at least not much, so long as the rotor system components do not change. The plot shows the rotor mode shapes. The horizontal axis is the location along the rotor system, and the vertical axis is the normalized angle of twist. A lump parameter model was used to create this plot, so those dots represent station numbers along the rotor. The lines show the shape of angular deflection across the rotor system. Generally, the steeper the line, the more stress there is at that location. Since the magnetostrictive sensor responds to stress, it is these locations with steeper lines that are ideal for sensor mounting. The mode shape diagram shows three modes. The blue line indicates the mode shape for the first, 1 crossing. The orange line indicates the mode shape for the second, 2 crossings. And the yellow line indicates the mode shape for the third, 3 crossings. For the first few modes of most turbo machinery systems, the steepest part of the mode will be where the mode lines cross 0. This is usually located at a coupling since these rotor elements are designed to provide mechanical fusing and avoid damage to more expensive and difficult to replace components inside the machine cases. For all 3 modes, the coupling area has 0 crossings and steep changes in mode shape, so this would be the preferred mounting location. On longer and more complex machine trains with multiple couplings, additional planes of measurement may have to be included to detect all of the lower modes. Having covered a few details on the application of the transducers, let's shift to a new topic and look at some of the data provided by the sensors. This slide shows data from a GE9H single-string combined cycle turbine. The thumbnail on the top right shows the machine train layout. The gas turbine is on the left and connects to a generator. The other side of the generator connects to a clutch, which connects to the steam turbine cases. The 5252 series probes were installed between the generator and the clutch. On startup, the gas turbine and generator reach operating speed first. During this mode, the clutch is not engaged so that the steam turbine can operate at slow roll while the HRSG comes to pressure. Once the HRSG has enough heat, the steam turbines can begin their ramp up. The clutch remains disengaged until the steam turbine speeds match that of the GT and generator. The clutch then engages and locks the 2 rotor systems together. Since it's impossible to perfectly match the steam turbine ramp rate to end exactly at the GT speed, there's a torsional impulse as the clutch engages. The data in this slide are taken from 2 distinct events. The data on the left was taken just after the probes were installed, and the data on the right was taken about 9 months later. One of the use cases for continuous monitoring of torsional vibration is to monitor the operating torsional natural frequencies and compare them against historical measurements or estimates from a model. If the torsional natural frequencies shift, this indicates a change in the stiffness or torsional forcing function of the rotor system and should be investigated. The left table shows the measured values as compared to the report values. The measured values were taken from the spectrum of the 5252 series transducers shown in the middle left plot. There's good agreement between the measured and report values, indicating the machine is operating as expected. The torsional vibration response at 4.2 Hz had enough amplitude that it could be seen in the rotor RPM plot shown in the bottom. In this plot, the blue line is the gas turbine speed and the red line is the steam turbine speed. In this mode, the gas turbine is 180 degrees out of phase with the steam turbine. The data on the right shows the second clutch engagement about 9 months later. There is a small change in the second mode frequency, but is not large enough to be a concern. Importantly, the spectral plot looks similar in shape and amplitude to the one on the left. The speed plot in the bottom also has a similar shape to the one on the left. This indicates the machine is operating as expected and hasn't experienced any unexpected changes. This slide shows data from an induction motor-driven compressor. In this train, the induction motor drives the centrifugal compressor through a speed-increasing gearbox. The mode shapes indicated that the low-speed coupling would be the best location for the first mode measurement, and the high-speed coupling would be the best location for the second measurement, so two planes were monitored on this machine. The focus was on the second mode, so the data on this slide is from the 5252 series probes located at the high-speed coupling. The plot on the left shows the time base in the top pane and the spectrum in the bottom pane. Gears can cross-couple lateral vibration into torsional vibration. Since the probes producing this data are mounted at the high-speed coupling, this appears to be the root cause of the components highlighted by the red dashed line in the plot. So these are not likely related to a torsional resonant response, even though they have relatively high amplitudes. The data shows spectral components that appear to be related to torsional vibration. The table on the right summarizes the results. The first row in this table is different and is labeled mode 0. This is the degenerate mode, and for systems without coupling to an inertial reference frame, this is usually not included in the report. However, turbo machinery with motors or generators can have coupling to inertial ground through the EMF in the motor. In this case, the EMF is strong enough to affect the torsional resonant response as reported by the probes, and so we've included it in the table here. The first column shows data from the model without inertial coupling, and the second column shows data from the system model with coupling to inertial ground. The third and fourth column show the measurements from the 5252 series spectra. Where there is enough amplitude, the values agree within 10%. This is more difference than would typically be expected, and root cause is under investigation. Now that we have seen some examples of how the data looks coming from the probes installed on the machines, let's move on to some of the analytics we can use to extract additional features from the probe signals. This slide covers three areas: stress monitoring, time-based amplitude calculation, and spectral domain feature extraction. As previously mentioned, the probes respond to torsional stress. Turbo machinery are typically designed to operate within the infinite life region of the material. However, machine malfunctions, machine startups, and other events can lead to higher than expected stress levels. Since the probes continuously monitor torsional stress, it is now possible to estimate the effect these stress cycles have on remaining life, assuming torsional stress is the dominant stress acting on the shaft. In this analytic, a rain flow counter is used to estimate the effect stress cycles larger than the infinite life limits have on the shaft. In the plot on the left, shaft life starts out at 100% and remains at this level as the machine operates, until the machine experiences a transient event with amplitude levels high enough to exceed the endurance limits of the shaft. Once the machine returns to steady state operation, the remaining life estimate again is constant. At the next transient event, there is another reduction in shaft life. In this way, it is possible to trend and monitor remaining life of a component. The middle section of the slide refers to the algorithm inside the monitoring system that continuously estimates the peak of the signal from the underlying waveform. This algorithm was tested against a number of transients from actual machines and models to be sure it can accurately characterize the transient event amplitudes, like the clutch engagement described previously. This plot shows how the different peak estimators compare to the original signal. Finally, the third column describes spectral band extractions. From the previous case histories, it can be seen how important it is to monitor and trend the amplitudes at and around certain frequencies. In spectral band extraction, a narrow band filter is used to extract the portion of the signal related to torsional vibration. In the plot, the top pane shows the signal with noise and other components on top of the torsional vibration signal. After spectral extraction, the middle pane shows the signal resulting from that extraction. This latter signal has only the information related to the torsional response with the noise and other components removed. We want to conclude with some thoughts on how torsional vibration further enhances machinery diagnostic capability. This slide shows data taken from a test kit instrumented with the 5252 series probes, left plot on both sides, and eddy current lateral vibration probes, right plot on both sides. The left side of the slide shows data taken with the shaft in new condition. The left pane on this side shows the 5252 series response as the torsional perturbator is swept through the resonant frequency. This frequency sweep results in the peak shown in the left plot. The eddy currents do not report a change in vibration, even though the rotor system went through a torsional resonance. It is this behavior that makes torsional vibration a silent killer. The machine can be in torsional distress, but this distress may not show up in the lateral vibration probes. The right side of the slide shows data taken from the same probe, but later in time after a crack has developed on the shaft. The inset in the top right shows this crack. It visually appears as a hairline fracture, and it can be difficult to see in this slide. The left pane again shows the torsional response as the torsional perturbation frequency is increased. The 5252 series probes show the expected torsional response and increase in amplitude as the excitation frequency coincides with the resonant frequency. This time, the eddy current probes also report a response, indicating cross-coupling between the torsional and lateral vibration. Interestingly enough, this lateral response shows up as 1x sidebands around the torsional forcing function. This is believed to be an artifact of the perturbator system. We want to conclude with an example of some of the testing we've done in-house to better understand how our probes respond as shafts are stressed and fail. Enjoy.
5252 series probes view a test spool installed between the load and drive motor. This scene shows the test stand in operation. Testing begins at no load and no stress on the test spool. A red line drawn on the shaft indicates the degree of twist as the test progresses. As stress and torque increase, so does the angle of twist on the shaft. This camera is mounted to the test spool. Observe how the red line has changed as stress and torque have increased. Switching to a stationary camera, the scene shows the two probes viewing the test spool. Torque and stress continue to increase. The test specimen fails catastrophically. The 5252 series probes provide continuous monitoring of the shaft up to and through the failure. The shaft failed along lines of plus or minus 45 degrees, consistent with torsional stress.
We are certainly excited to be introducing Benton Nevada's next chapter in rotor dynamics. Wish to thank each and every one of you for taking the time to listen in to this short presentation. Let's now open it up for questions and answers.
Okay, the first question I have here is, are there any special surface requirements? Brian, do you want to take that?
Oh, thanks, John. So for this probe, the application is very similar to an eddy current probe. We can view an unprepared shaft and get a good response out of it, but we'd like, if possible, to burnish the area. Thanks, John.
Perfect. Can you determine when or if my shaft will fail? Chris, you want to take that?
Sure, John. So that's kind of a bit of a tough question to answer. Yes, we can determine it if it's related to torsional vibration, right? You know, we're not accounting for, the Vorso program doesn't account for any other, you know, bending moments, et cetera, that are coming through. But from a torsional perspective, we can provide some of the outputs some like to call it a rain flow counter, if you will, or basically the stress cycle curves coming through. So if it's truly torsional related, we can certainly provide some leading indicators and counters for that.
Right. Okay. Are nodal points identified by experimentation? And Brian, shift that one to you.
Thanks, John. The way we've been approaching this is most turbomachinery, we get a torsional model, and it tells us what the nodal points are based on the lump parameter mass or maybe a finite element. That tells us where we want to put the probes. Once we get the probes installed, assuming we're doing multiple planes, then we can look at the phase differences and get a good sense of where the actual nodal points are.
Okay, great. Does the Vorso output both torque as a DC and torsion as an AC for analytics in System 1?
Oh, sorry, John. I'll take.
I'm sorry.
I'll take.
I forgot to toss that to you.
Or both of us, Brian or I, can kind of handle that one. So,
Yeah.
So certainly the AC component, that's the torsional vibration coming through in the System 1. And yes, you can trend the DC component or trend the overall torque values. Again, I'd say for trending purposes only in System 1, we wouldn't recommend using it, at least in this first release here, for anything beyond just the trending purposes. Our primary focus, again, is on the torsional amplitudes or torsional natural frequencies that are coming through.
Okay. Brian, on to you. What is the accuracy of the oscillating torque values?
So we look at this probe a lot like we do an eddy current probe. An eddy current probe provides you DC coupled vibration signal for lateral motion. We want to provide a DC coupled signal for torsional motion. So what we're doing here is targeting a similar level of accuracy. So an 11 millimeter XL system is plus or minus 6.5%. For the Vorso system, we're targeting plus or minus 10%.
Okay, great. Chris, this next one is for you. When will this be available as a diagnostic service?
As a service? Okay, well, I'm going to answer this in twofold, but I'll answer the first one. As a diagnostic service, so the Vorso, again, will be introduced not only with Adre, that's our diagnostic services piece. We're targeting to have that released by about mid-2022. And then, of course, as we roll into the full continuous use with either 3500 or Orbit 60 would follow suit after that. So from a service perspective, you're looking at about mid-2022.
Okay, great. Brian, is the bridge sensor inherently temperature compensated?
Thanks, John. So one of the things that this topology with the 4 individual sense coils gives us is a good opportunity to reject any sort of common mode noise, any sort of common electromagnetic interference, and to some extent temperature that we can reject. And then any other compensation that we need to do is done in the interface module.
Okay. Chris, are there different versions of Vorso for different shaft materials?
Great question. So, as we go to release, we're going to have 2 or 3 different most common shaft materials out there. So you'll just need one version of the Vorso. However, if there are, very specific shaft materials not listed on our data sheet or not as a part of our initial release, as one of those key components, it would be an update or a change really to the calibration in that interface module. Granted, that would most likely be a custom unit. We'd certainly have to evaluate that as they're out there. But again, we're going to be looking at probably 3 of the most common shaft materials that we see. But as we all know, as soon as we release those 3, there's going to be several others that come in. We'll need to evaluate as we go. But again, just one Vorso for those 3 most common, and if it's outside of those parameters, it would be a custom.
Okay. For the installation, is there any special requirement on the angle alignment, space between the rotor and sensor tip? And Brian, I'll pass that one on to you.
All right, thanks, John. That's another great question. The way this probe installs is similar to an eddy current probe. So we establish an air gap between the surface of the probe and the surface of the shaft. Alignment is typical alignment requirements that you'd have for an eddy current, so plus or minus 6 to 7 degrees, all mechanically aligned. The one thing that'll be a little different is during the commissioning, we're going to have to take readings at a couple different gaps. But other than that, the installation will be similar to an eddy current. It is going to be a little bit wider than the eddy currents, probably on the order of 25 to 40 millimeters. So you'll have a little bit more shaft space, but other than that, installation is similar.
Okay, great. This next question is, how do you determine alert and danger levels? And Brian, do you want to handle that one as well?
Sure, John. So, and it might tie into the question above as well. So, as you know, in Nevada, we typically defer to the OEMs and their recommendations for the stress levels. So, if you have a machine, we'd recommend you consult with the OEMs and work with them. You know, in the absence of OEMs, what we've been following is basic stress cycle calculations and counting using Miner's rule. So if you know the shaft material, which we should know for the probe, we can step you through what that kind of approach would give you for alarm settings for that rain flow counter, that stress cycle counting. And then for the amplitude levels on the spectral bands, that's the other thing that we're going to be looking at is specific spectral frequencies. We'd look again at what those stress levels, how those relate to that inferred stress on the shaft, and making sure that you're staying in the infinite life region of the shaft. Hopefully that was helpful.
Yeah, I think so. And so we have another one here. How to determine where to install the Vorso, for example, the axial position on the shaft?
Do you want me to take that?
And I'm sorry. Yes, that would be great.
Okay. So, kind of referring back to the model, if you look at the torsional modal shapes, what we want to do is install these shafts at a point where the torsional stress is highest. So those mode shapes, it's usually looking at the rate of change. And for most of the machines we're looking at, that's occurring at the nodal point. It's typically at the couplings because those are the mechanical fuses in your system. And that's where we get the highest stress and the best response to torsional vibration.
Okay. And Chris, what assets or industries are the primary candidates for this system?
We touched upon it briefly in the presentation, but I'll just kind of reiterate a few of these. So, I mean, torsional vibration really affects, any machine or machine trade asset that's out there. I'd say, the primary first targets that we think this Vorso would be most applicable to, certainly out there, is a couple of fold. One, certainly, any motor-driven, asset, whether it's a compressor or anything else out there, especially motor-driven assets that have a variable frequency drive on them. Variable frequency drives offer tremendous efficiencies, becoming more and more in use that are out there, but just by their very nature, these variable frequency drives can introduce, again, very minute, but can introduce some of these torsional oscillations and vibrations that are coming through. And that's one of the primary reasons we're seeing an influx or an increase in torsional-related failures on these machine trains. Another great application for Vorso is certainly power, right? Any power turbine, steam turbine, or combination of the two coming out there as these units, engage, fire up, startup, shutdowns, even continuous use coming through when you've got grid fluctuations coming in. There's certain regions, obviously, with renewable powers coming on, or with wind, there's a bunch of these fluctuations coming through, and that causes oscillations, throughout that machine train that can cause some issues. And then really for any large, rotating equipment, that's out there. A lot of times, and most of the time, you should be asking, your OEM of that particular piece of equipment, either for a torsional report, those torsional nodes. I think somebody was asking about torsional nodes a little bit earlier. Whether that's a mathematical model that the OEM provides, or whether there's a physical study that's done. That's fantastic to have. But once that piece of equipment, is out in the field, typically you're going to install that or connect it to something else, whether it's a gearbox, whether it's a compressor, whether it's something else. Obviously adding additional components to that entire machine train is going to change things as well. So having that peace of mind on those large rotating assets is another application. And I'd say there's a large market here for torsional oscillations that we didn't cover in too much detail. That'll be a focus of ours. After we get this first release out, is quite frankly the large reciprocating market, right? That's out there. So there's quite a few applications here that we see torsional vibration.
Great. I'm especially waiting for the recip one. Next question to Brian. Is there an oscillator demodulator like proximeter involved for the Vorso?
Okay, yeah, we might have mentioned this in the presentation. The architecture for this system is going to be somewhat similar to an XL in that you do have a 3300 XL probe and that you do have a probe mounted local to the shaft. And actually in this case, we're going to have two probes mounted at each plane of measurement. Both of those probes are going to come back to a single interface module. And it's the output of that interface module that has the DC-coupled torsional vibration signal.
Okay. I think this last question is really a comment, but we'll go ahead and put it out there anyway. It says not all shaft trains have torsional model in reality. End user will need a better guide to where to install the Vorso in this person's view. So, and that just goes back to the comments you've made.
Yeah, I think
what's that?
I think we can add a little color to that as well. It's a great comment. Yes, you're absolutely correct. Whomever asked that. Not every machine train or piece of equipment or shaft train has that torsional model readily available or even provided by the OEM. So yes, it comes down to engineering prudence. I know Brian touched upon that a little bit earlier of these nodal points, but one of the advantages that we see as a general rule of thumb in any machine train, typically, you've got couplings, right? You've got to join the two units. Your coupling, you want to be, well, you don't want any couplings to fail, but if you're going to have the shaft failure, you're going to want it to be around those coupling points, a little bit easier to access, of course, rather than being buried inside of the machine. Typically, if you don't have a report on these nodal points, our recommendation is always to look around the coupling area. One, it's easier to access, number one. Number two, it typically has the highest degree of stress, therefore torque, for the sensor to be the most effective. So there are means around it versus just having the full torsional model.
Great.
Thanks, John. Add a couple.
No, I appreciate that. And I should have mentioned that was our last question. I haven't seen any others come in. So I'm going to thank everybody for attending today's webinar on Vorso, Bentley Nevada's latest sensor measuring torsional vibration. If you have any additional questions or would like to receive professional development hours, please contact your account manager. And if you would like to learn more about using System 1 or machinery diagnostics and are interested in attending one of our formal courses, please visit www.bentleytraining.com. And while we have begun offering several courses in person again, System 1 and machinery diagnostics are still available as online virtual training courses. If you would like to watch a replay of today's session or suggest it to a friend or colleague, you can find a link to it in the related content tab on your console. I will caution you, however, that the replay won't be available until about half an hour from now. In the meantime, the related content tab also includes registration links to our next webinar, as well as a PDF of today's training materials. Also, you can always log back in here later to get to the resources tab. You do that by clicking on the link in your original calendar invitation. And one last but important thing, a survey will pop up on your console after the webinar concludes. Please fill it out as we value your feedback. In fact, it was because of this feedback last year that we launched these Beyond the Basics webinars. Again, thank you for attending and have a great rest of your week. Take care.